Data and Math, Finite Field Symmetry. In the last video, we constructed the following matrix, which is designed to allow for coefficient collapse on row differentiation. Its construction is very simple, which is the goal of this lesson. I call it an elective power matrix because we can select how it is constructed. The parameters we can use to construct this matrix are, first, the right side must be constant, and the top must be iterating. But the top doesn't have to be the powers of 2, like in this example, or the right side, 1. The right side could be 5, for example, and the top could be the powers of 7. I'm not sure about all permutations of this matrix, but I do know that powers as the top row work. Matrix properties. It is constructed from custom sequences. It is row reducing, and it's because of this row reducing that it has a polynomial form. It matches the triangle expansion exactly, and it only extends in blocks that are powers of 2 in length. That is to say, if I have a sequence of 5 numbers, when I evaluate them as a function, they will repeat after the 8th index. Here's it constructed abstractly. A, or our constant term. B, A plus B. C, C plus B, C plus A. D, D plus C, D plus B, D plus C plus B plus A, and so on. We can turn this into a matrix by repeating each row as a column, continuing until we are square. Let's look at an example. Take 5 numbers, build a number triangle, extend the furthest column, in this case we have 3 new values, and if we try to continue, the pattern will repeat. Keep this number triangle in mind as we look at the next slide. Here's the initial data column. At this point we can introduce our elective power matrix, and we reduce. Using the triangle from the previous slide, we can begin to evaluate a polynomial. Summary. I like to call this the poor man's method. It's so easy and simple that you can actually do it on paper. We can implement it with only the XOR operator. We don't actually need finite fields or multiplication over them. And furthermore, we can implement encryption and error correction without a finite field if we can finesse the data into block sizes that are powers of 2, which is an easy feat. I'll note that the symmetry of this method isn't perfect. There are some catches that we'll encounter shortly. My favorite part about this, even though there is an issue with the symmetry, is that it can be done on a piece of paper. And we can work around the issues in the symmetry. We can learn encryption on paper. We can learn error correction on paper. And we don't need code libraries or to even know how to code to comprehend those concepts. Web Demo and JavaScript API available at math.d8data.io.